So yesterday I tried to talk about just a couple, some of the techniques we have in this subject to do anything. The first was I talked a little bit about if I have a torus action on X, and let's say if X is toric, I have a big three-dimensional torus acting on X, and I work everywhere now with equivariant cohomology. Then I can use some localization techniques to get some kind of combinatorially kind of insane expression for the invariance that we're interested in. But it's something that, for instance, is completely codable, so it allows you to actually do some kinds of checks and things like that. And it also gives kind of an in-principle way of understanding anything you want, but it's just hard to actually use that by itself because the combinatorial difficulty just gets bigger and bigger the further into your generating function you go. One thing I forgot to say yesterday, so this is the first topic. One thing I forgot to say yesterday was that this also gives you a way of doing of defining integrals on some kind of non-compact space. So before, the way I think about doing integrals is I'm doing some kind of proper push forward in cohomology. If X is non-compact, it's no longer a proper push forward to a point. But as long as xt is compact, the fixed locus is compact, then I can still define, just using this Atiyah-Bott localization, I can still define a map from, well, I guess I was doing everything in homology I'm doing. So to speak. I could define a map like this after I tensor with this fraction field. So to speak, once I move to the field of rational functions. And the idea is that after I tensor with the fraction field, this is the same as the equivariant homology of the fixed locus, and this is proper over a point, so I can push forward from here. So the result is this gives me a way of defining some kind of integrals, but they're going to take values in the field of rational functions. And this is a good flexibility to have because almost most of the geometries where we can compute are going to be non-compact. Okay, so this was the first topic. And then the second topic, which is where I'm going to continue now, was this idea of studying not just the Donaldson-Thomas theory of a threefold, but actually a pair, threefold and the smooth surface. And so we talked about this space of relative ideal sheaves. I have to be honest, I haven't really been looking backwards at my notes, so I feel like the notation has been changing. So I'm not sure if sometimes maybe I put a comma here. Anyways, I'm just going to throw up a bunch of letters, and hopefully from context it'll be clear what I mean. And so, okay, so this was some kind of space of relative sheaves, relative ideal sheaves. And the whole point of this space was that I'm only considering subschemes that meet this divisor D cleanly. And in order to compactify, I have to allow myself the option of not just considering sheaves on X, but sheaves on this kind of bubbled version of X. So this is the kind of object in this space. So the motivation for this kind of object was the original motivation has to do with some kind of degeneration formula, where I take a complicated threefold and I degenerate it to two simpler ones. But actually, that's not really how we're going to use it. Because for us, X is going to be like P3, so it's not like you can degenerate P3 to anything really much simpler. The reason that this space is so nice is that it comes with some extra structure maps. So the first was this map to the Hilbert scheme of points on D itself. This was obtained by taking my subscheme and just intersecting it with the last copy of D. So if you like this. And because of this condition that I'm intersecting this divisor cleanly, this is a sensible thing to do. Otherwise, I would need some kind of derived tensor product here. So this is the first nice map. And the reason why this is a nice map is that this is a smooth projective or quasi-projective variety, and we know everything about it. We understand its cohomology very well. And the second structure map, so again, so an element of this space is a choice of target, and then an ideal sheaf on it. So then the second structure map is this kind of weird one where I forget everything except for which target I'm on. And this takes values in this stack T, which is a stack of target degenerations. And as I explained at the end, one way, if you want to think about what this stack looks like, one way of thinking about it is there's actually an open substack of the stack of three-pointed genus 0 semi-stable curves. And this is going to be a very useful fact because it means that anything that we can do using the cohomology of genus 0 of the moduli space of genus 0 curves will give us some kind of structure here in this relative dt space. So let me give the first example of this. So this idea that you would translate the recursive structure of this moduli space into some kind of algebraic structure is really the center of studying quantum cohomology, and so all of those same ideas translate into this setting. So this is some kind of application of this idea. So it has to do with some kind of version of the quantum ring. So I'm going to fix some number n. I fix a smooth surface S. And I want to look at the threefold that is just S cross P1. And my relative divisor is going to be 3 fibers of this. So again, the way you can think about this is that so this is S, and this is the P1 direction, and I've singled out 3 of the fibers. One thing I didn't say, strictly speaking, in this kind of definition of this space of relative ideal sheaves, if D is disconnected, as it is here I have 3 things, I want to bubble them off independently. That's strictly speaking not the way I defined it yesterday, but I'd like to imagine each fiber here has its own set of bubbles. And so in particular, this is the space before I've done any bubbling. Once I start bubbling it, if you look at it kind of vertically, I get something S cross one of these kinds of curves. If that picture makes any sense. So are there any questions? Okay, so just like I did before, I'm going to write down this space. And the curve class, well, I'm going to fix a curve class on my surface. And then I can get a curve class on my threefold just by taking this class on the surface plus, this number of P1 fibers. And because I have these 3 relative divisors, I have 3 versions of this horizontal map up there. So I actually have for 0, 1, and infinity, I have a map from this space to the Hilbert scheme of S and the number of points in the Hilbert scheme is going to be the intersection of this curve class with this divisor. And so by construction, it's the Hilbert scheme of n points on S. Okay. So the goal now is to use this structure to construct something that very much analogous to the usual quantum product. So I'm going to use these maps. These are going to be like just the evaluation maps when I do genus zero Gromov-Witten theory. So I'm going to pull them back and then, integrate. So what do? So I fix three classes in the cohomology of my Hilbert scheme. So maybe I can simplify my life by putting times 3 here. And I'm just going to put everything in this big generating function. So chi is going to be, again, the Euler characteristic. I'm going to sum over curve classes. This capital N is always going to be fixed, though. And then I take this relative dt invariant. With this insertion. So okay. So this is some huge thing. Which I'm going to abbreviate like that. Mm-hmm. Yes, I'll get there in a second. Yeah, and I mean I'll be honest. I've probably been a little sloppy about like the kind of degenerate terms, but the claim, as Jan pointed out, yeah. So I can already tell I need to shift Q slightly to get this to be actually correct, but I can absorb it into the pairing. So the claim is that. If I change the inner product on the cohomology of the Hilbert scheme correctly, then these are actually going to be structure constants. Of a ring over Laurent series in these variables. Not only that, it'll be a deformation of the classical cohomology ring of the Hilbert scheme. Okay. And the proof of that, so the proof of that is just identical to the proof in quantum cohomology, which is that the way you can think about the argument in quantum cohomology is that I write down some relations, cohomology relations in the moduli space of genus zero curves, and then I pull them back to my space of stable maps. My virtual classes behave well with respect to splitting and things like that, and something that looks like associativity just falls out. And so the same thing happens here. So the same happens here. The way you can think about it is that these spaces of relative maps, of relative sheaves, always carry maps to M03. If I take a fourth relative point, instead of taking 3 relative fibers, I take 4 of them, I'll get a map to M04, and then I can play around with that. There are 2 rationally equivalent boundary classes in the cohomology of M04, and I pull them back and I get the associativity relation So I'm not actually going to prove this. I just wanted to sketch the idea. Yeah, so I mean, all proofs are going to be sketches of proofs. I mean, unless it gets really sketchy, and then I'll actually write down the word sketch. Oh yeah, you're just reading out my. Yeah, this is the next thing I'm going to say. Yeah, right. Okay. So the natural question, which is that okay. So what have I defined? I've defined a ring deformation of the classical cohomology ring. The number of variables is, so to speak, curve classes on the surface plus 1, which is actually also the number of curve classes on the Hilbert scheme of S. There's the curve classes on S plus 1 coming from. Well, this with the Hilbert-Chow map. So maybe I can say that. So B2 of the Hilbert scheme of S, assuming I have more than one point, is B2 of S plus 1, and that extra curve is the fiber of the map from the Hilbert scheme to the symmetric power of S. This is some singular object, and this is a resolution of singularities. And there's a unique curve class that's in the fiber of this map. And that gives me the extra 1. So not only this is a ring deformation, it's a ring deformation in the same number of variables as the classical cohomology ring. And so you can just naturally ask, how does this relate? The usual quantum cohomology ring. Question mark. So I'm about to lower this board, so if you have any questions about what's written here, now's your last chance.